let's take a look at the concept of digitization.
The world we live in is inherently analog. That means the signals are continuous, both in time and space. However, computers are inherently digital. So, Professor Yarabali, how do we capture analog signals in a digital form?
That is right. So we have our computers. For us, it's a microcontroller, which is inherently digital because it stores information in the form of binary data. And we have the analog world, which conveys information as a continuous time varying signal. And we have to interface these two. So our first kind of interfacing is how do we read information that's analog and store it in digital form. So what we need is a conversion, which we call analog to digital conversion, ADC, which does that act for us. The second possibility is when we want to affect the world that is analog, and the affectation is performed by, again, a microcontroller. So we have the information in digital form and we want to convey it to the outside world, which is analog. And we do that by introducing a module which we will call a DAC. A DAC is a digital to analog converter. In some cases, the DAC could be part of the microcontroller, but for flexibility, we will use external circuitry that will do the job for us. So let's take a look at some examples. So when I look at examples of analog stimuli that have to be captured in digital form, I can think of simple things like temperature sensors, sound, which is where we're doing recording, we're capturing sound, and we can think of pressure sensors.
There are signals in the body, biopotentials you could measure.
Okay, bio sensors. We can think of proximity sensors.
I don't want my robot to hit the wall.
Yeah. And we have optical sensors. Now, the world of embedded systems is all about being able to work with sensors. But we also have the counterpart, which is actuators. So if we call these sensors, which is the input part, then the output is actuators. That is, we produce a stimuli which affects the world. So again, we can think of examples like controlling our motors, so that we send voltages that power our motors.
Sound could be an output too.
Speakers. We could have lights, dimmers, for example. What else?
Pacemaker uses an output to trigger the heart, so it's another biosensor, a bioactuator.
Bioactuator. And our anti-lock brakes are outputs. And we want the braking to be controlled. It's not a on-off thing, but it's something that is that has to be a variable. So that's one.
Just like temperature was an input, it could be an output. So our heating and air conditioning.
So AC could be. So we have examples of sensors and actuators. So in summary then, we have the analog world interfacing with our digital computers and we have our ADCs and DACs that accomplish that. So this module is going to be focusing on DACs.
What's next?
So our next goal is to understand what the fundamentals of digitization are. So we saw that the purpose of digitization is to take an analog signal and digitize it, which means that to store it in a computer. So we have an analog signal that's continuously varying in time, and for now we will think of it as a changing voltage, and we want to digitize this. So digitization is done using two concepts. One is our amplitude quantization. So by quantization we mean discretizing the signal. So we have continuous, the opposite of continuous, that as far as the computer is concerned is discrete. So when we store our information in the computer, we store them as digital values. So our amplitude quantization is talking about separating our amplitude into levels. So we'll call these levels. So the counterpart to amplitude quantization is to do time quantization, which is also referred to as sampling. So time quantization is capturing the signal periodically, or as we say, sampling the signal, so that we can capture the essence of the signal faithfully. So we have periodic capture of samples, which we call as time quantization. So let's look at what the trade-offs are when we do amplitude quantization and time quantization. So the way we like to look at this is, if I have more levels, from a computer standpoint, I have to represent this by more bits per sample, which means I have more levels. If I have only 2 levels, I would represent all samples by just 0 or 1, but more levels means more bits per sample. From an analog standpoint, what this means is I have better precision. So we'll define the term precision. The term precision is telling us exactly the number of levels we can represent in a signal. So I'm assuming that I have around 16 levels here. If I have 16 levels, I have 4 bits per sample, so the precision is 16. Now, what I also have is this concept of resolution. Resolution is the smallest change I can represent in the analog signal. So resolution is the smallest change, which means it's the difference between levels that I can actually capture. So what we are saying is this captures precision. Now, what we also see then is if we have more samples, then or the rate of capture is high, then what we're saying is from a computer standpoint, we need faster processing, whether we're producing these samples or we're capturing these samples, we have to do more processing per unit time. What it means from an analog standpoint is the more samples I capture, the more faithful the digital representation is with respect to the analog signal. As a matter of fact, we will capture this idea of faithfulness using a theorem called the Nyquist Theorem, which for us simply tells us how faithful is faithful enough. That is, how many samples per second is best to capture the essence of the analog signal. So in summary then, digitization is about taking a continuous time varying signal and discretizing it so that we capture it by these discrete points that attempt to make a faithful representation of the signal.